Have you ever had a super fast piece of tech just glitch out on you for no apparent reason? Well, there's a good chance the culprit is this sort of ghost in the machine, a concept called impedance. And today, we're going to figure out how to tame it. So here's the plan. We'll start with those annoying high-speed glitches, then we'll dig into what's actually causing them, these echoes in the wires. And finally, we'll check out the cool engineering tricks used to get rid of them for good. All right, section 1, the high-speed glitch. In your basic electronics class, they teach you that circuits are pretty predictable, right? But here's the thing. As our devices get faster and faster, that simple, neat little model, it just completely falls apart. So in theory, you flip a switch and bam, the voltage gets where it's going instantly. Simple. But in the real world of high-speed electronics, that's not what happens at all. If there's any distance between that switch and the component it's talking to, there's a travel time, a delay. And it's this delay, this travel time, that leads to all sorts of bizarre problems. You get these weird signal distortions, things called ringing and stair-stepping. And what does that mean for you? It means false triggers, corrupted data, basically a total mess. Okay, so what is actually going on here? How do we get these echoes? Well, it turns out that at really high speeds, even a tiny little copper trace on a circuit board stops behaving like a simple wire. It starts acting like a full-blown transmission line. And that changes everything. See, every one of these transmission lines has this built-in fundamental property. It's called characteristic impedance, or Z0. Think of it as the natural resistance that the line presents to a signal traveling down it. It's the absolute key to this whole puzzle. And here's where the trouble begins. When that signal is cruising along and suddenly hits a point where the impedance changes, like when it gets to the chip at the end of the line, you get a mismatch. And that mismatch acts like a wall. Some of that signal's energy has nowhere to go, so it bounces back. It reflects. You literally get an echo in the wire. So the million-dollar question is, how do we stop these echoes? How do we silence them? The goal is to make sure that when the signal gets to the end of its journey, it doesn't hit a wall. It needs to end smoothly. And the way we do that is, honestly, kind of brilliant. We basically trick the signal into thinking the line just goes on forever. We do this by making sure the impedance of the component at the end, the load, perfectly matches the characteristic impedance of the line. When they're the same, all the signal's energy gets absorbed. No mismatch, no reflection, no echo. Problem solved. Okay, so how do engineers actually do this in the real world? Well, they have a whole set of tricks up their sleeves. And these techniques are called termination. Let's open up the toolkit and see what's inside. First up, the classic, parallel termination. This one is super straightforward. You just connect a single resistor at the end of the line, right at the destination. And if that resistor's value is the same as the line's impedance, boom, the signal gets absorbed perfectly. Now, series termination flips the script. Instead of putting the resistor at the end of the line, you put it right at the beginning, right next to the chip that's sending the signal. It's also called backmatching, and it works a bit differently to solve the same problem. Then you've got Thevenin termination. Now, this one's a bit more clever. It uses a pair of resistors to create a voltage divider. The cool thing here is that the parallel resistance of this setup is what matches the line, and it can actually help a chip that doesn't have a lot of oomph, a weak driver, to keep the signal looking nice and clean. And for a totally different way of thinking, check this out. Diode termination. Instead of trying to prevent the echo from happening in the first place, this method just deals with the consequences. It uses super fast components called Schottky diodes to literally just chop off the tops and bottoms of those nasty voltage spikes, the ringing that the reflections cause. So as you can see, there's no single perfect solution. Each one of these techniques has its own pros and cons. You've got trade-offs in power consumption, how complex it is to design, and how well it performs. The right choice really depends on what you're trying to build. Okay, so we've got the theory, we've seen the tools. Let's put it all together and see why this matters so much. Because this isn't just some abstract physics problem, right? This is at the very heart of designing modern electronics. Everything from the processor in your computer to the RAM it talks to. Take a look at a basic circuit, like this simple amplifier. The same principles apply. You have to carefully manage its input and output impedances. Why? To make sure you get a clean signal out, and just as important, to make sure you're transferring the maximum amount of power from one stage to the next. It's all connected. So here's the bottom line. As we push our electronics to be faster and faster, these weird, invisible effects, these transmission line problems, they stop being a minor issue and become the main issue.
Understanding and mastering impedance isn't just a nice-to-have skill for an engineer anymore. It is absolutely essential to making our high-speed world actually work.